Okay, everybody, welcome back. Um, Taking a look at periodic trends in Chapter 10. So it says both an element's position in the table and its properties are a direct result of its electronic configuration. Well, we already know some of that because we said that, for instance, all the Group 1 metals have the same type of chemistry. All the Group 2 metals have the same type of chemistry. So we know going down a column, we have similar chemical reactivities, similar products that we get from chemical reactions. But there's also physical properties as well that we can predict. Some of them we already know, like we know where the metals are on the periodic table and we know where the non-metals are. But there are other properties as well, and that's really what we're going to get into. So in this first video, I'm going to explain the physics behind it, and then we'll look at the actual trends in another video. The properties are predictable and repeat themselves. They are based on electronic configuration. All right, so two things we have to consider. One, what is the strength of the nucleus pulling on those electrons, and where are those electrons in regards to their orbitals? All right, so a little bit of background here. All right, periodicity. So we are going to predict properties based upon where an atom is on the periodic table. And there's three ways of looking at these different periodic trends. One, down a group. We're going to compare things that are in the same group, the same column, as we go from the top to the bottom of the periodic table in that column. And so this is called, of course, a group trend. Or we could take a look at comparing materials that are going from left to right in the same period. So again, from the left of the table to the right. And this is called a period trend. Third, we could take a look at what's called the diagonal effect. But the diagonal effect is something that you would study maybe in your second year of college. And the diagonal effect would be, for instance, if we have oxygen here on the periodic table, and then we have chlorine over here, fluorine and sulfur, then we would say that this is the diagonal effect. And again, that's advanced, that's second year college, so we're not going to be studying the diagonal effect, just the group and the period. Now, all of these trends can be explained by Coulomb's law. Because what we're doing is we're looking at the force of attraction between the positive nucleus, and we want to consider the outermost electron, or the valence electrons. So Coulomb's law, we know the force of attraction is equal to proportionality constant, Q1 times Q2 over D squared. So remember, Q1 is the charges, but in this case we're only going to focus on the positive charge, the charge from the nucleus. That's going to be the most important factor. And then for D squared, this is the distance between charges, so what we're going to focus on is the outermost electron. Now, I probably shouldn't use equals here. Okay, when we're talking about period trends, so I'm going to do a little squiggly, meaning approximately. When we're talking about period trends, we're going to focus on Q1 and Q2. That's going to be the most important thing when we're talking about period trends. And when we're talking about group trends, the most important aspect is going to be that distance between the nucleus and the outermost electrons. So do understand that they're in the same chemical equation with each other. So when we talk about not chemical equations, I mean the same equation as each other. So when we say that we have variables in the equation, what it means is that they are in concert with each other. In other words, for every periodic trend, whether we're talking about a group trend or a period trend, you do have both the charges and the distance between the charges interacting. But when we say a period trend, even though there is a distance between the charges, we're still going to focus on Q1, Q2. That's going to be the most important thing. And we're going to ignore D squared. Same thing with the group trends. We're going to focus on D squared, and we're going to ignore Q1, Q2, because even though there are charges, it's not the most important aspect. When we deal with period trends and we deal with this positive charge for the nucleus, we're going to call that Z effective nuclear charge, or charge density. And when we deal with the group trends, we're dealing with the quantum energy number and the fact that we have shells underneath those outermost electrons, and those shells create an effect that we call shielding. And we'll get to shielding in another video. So let's say, for instance, we're dealing with a trend called atomic radii. All right, what is the atomic radii? The atomic radii is the distance from the nucleus of an atom to its outermost electron. Let's call that R for atomic radii. So that distance. Well, what affects that distance? If we look at the periodic table, I'll draw my little periodic table here. All right, kind of looks like this. As we go from top to bottom on the periodic table, the atoms get larger. In other words, the atomic radii increases as we go down any particular group. So if we were to examine group 1, for instance, the S1 column, we would say that hydrogen has a smaller atomic radius. I'm going to abbreviate this AR for atomic radius. Hydrogen has a smaller atomic radius than lithium, which has a smaller atomic radius than sodium, which has a smaller atomic radius than potassium, which is smaller than rubidium, which is smaller than cesium, and which is smaller than francium. Now, we said all group trends like this we can explain through D squared, quantum energy. So let's look at the quantum energy number. Where's the outermost electron in hydrogen? It's a 1s1 configuration. Lithium is 2s1, sodium is 3s1, potassium is 4s1, etc. So it makes sense to us that as we go down a particular column, that the atoms get bigger compared to the one in the one previously above it. And again, that's because we're increasing quantum energy. And if we're increasing quantum energy, then we would say the outermost electron is shielded by a core. The bigger the core, the more shielding you get. And the further away from the nucleus the electron becomes. So it makes sense to us, this trend, that the atoms are going to get bigger as we go down the table. And it goes with our intuition, because you're adding more electrons. And as you're adding electrons, you're filling energy levels, and the electrons are getting further and further away from the nucleus, the outermost electrons, that is. But the trend as you go from left to right is not what you would expect. So again, we draw a little periodic table. Here we go. Make it look fancy. Okay. So let's look at period 4, for instance. And period 4 starts with potassium, and then you have calcium and scandium, and then it goes all the way across to bromine. Now, we're going to ignore column 18. Once you get a full octet, the electrons tend to spread out and stabilize, so the trends for group 18 aren't the same as the trends for the rest of the periodic table. So we're going to ignore group 18. As we go from left to right, the atoms actually get smaller. Atomic radius decreases left to right across a period. All right, so the period trend for atomic radius is that the atoms get smaller as you go from left to right. Now, intuitively, that doesn't make sense to us, because if we look at potassium, potassium has 19 protons, and so that means it has 19 electrons, whereas as we go across to bromine, bromine has 35 protons and electrons, so we would expect bromine to be much bigger, but it's not. And the reason why is if you look at their highest quantum number, potassium has an electron in the 4s shell. Bromine has electrons in the 4p shell. The highest quantum number is still 4, which means that it has a certain amount of quantum energy. So why on earth then is the atom actually getting smaller as we go from left to right? Well, it has to do with Z effective force. Think about it. Bromine has 35 protons, whereas potassium only has 19 protons. So the 35 protons, this is a much stronger pulling force. And that pulling force is only distributed over the fourth energy level. So when you look at the outermost electrons, bromine is actually sucking in the outermost electrons closer to the nucleus than potassium is. Now, it's not much of an effect. They get slightly closer. So potassium is a slightly larger atomic radius than calcium, and calcium is slightly larger than scandium, and scandium is slightly larger than titanium, and then we'll go all the way across to selenium and then bromine at the end. So bromine is the smallest, despite the fact that it has 35 protons. Why? Because of that increased charge. So we go back to our force of attraction. Q1, Q2 over d squared. Which one is going to have a larger force of attraction? 19 protons or 35 protons? Well, it's the 35 protons in bromine. So that creates a larger force. And that means that the electrons get sucked in slightly closer. And all periodic trends that we study are going to be explained based upon these two concepts. If we're talking about a period trend left to right, it is always going to be explained based upon pulling force, Z effective force. If we're talking about group trends as we go down the column, they're always going to be explained based upon quantum energy and shielding effect. And that's really it. If you fight that, you're going to have trouble understanding it. But if you accept that all period trends are based upon Z effective force, that all group trends are based upon quantum energy. For instance, let's say we have a periodic trend for acidity. You don't know what that is yet. So the trend in acidity is that acidity actually increases as you go down the group. So why would hydroiodic acid be more acidic than hydrofluoric acid? Well, it's because in hydroiodic acid, you have a larger radius, and therefore the charge is able to disperse, and it's more acidic in its nature, but you don't need to know that. All group trends are based upon d squared. So if we go back to Coulomb's law, we would say, look, why is hydroiodic more acidic? Because d squared is larger due to more quantum energy, which results in less attraction between the nucleus and the outermost electrons. And that's it. All right. Thank you very much.